Alright, Assalamualaikum warahmatullahi wabarakatuh, and hi to everyone. So let us start with our topic number one of Polyphase Circuit, and now is the introduction to Polyphase Voltage Generations. Again, thanks to Dr. Muhammad Noor bin Abdullah for his kindness sharing these slides and some of the content outlines. So single-phase voltage generation will be the first subtopic, followed by two-phase voltage generations, as well as three-phase voltage generation. And we will look at the single and double subscript notation. And this is the learning outcomes. So after completing this unit, you will be able to know the differences between single-phase and three-phase systems. So be familiar with the different power system configurations. So the overall or the overview of power system, so supply system and per unit system, power system study notes for electrical engineering. So you can see we start with the power plant over here. All right, let me change to laser pointer. So we start with power plant over here. So we generate energy or electricity with the value of 12 kilovolts. So we move on to the step-up transformer before it goes to the long transmission line that carry high voltage up to 400 kilovolt, and then we step down at the substation, which is down to 13 kilowatt. All right, and then again distributed to the residential area, for example, and step it down again down to 240 volt. All right, so this is how it works for the supply system, or we simply can say that from generation, up to the residential area. Right. So next, so this is again the details explanation or illustration you can understand. So we have the generation for A, so power stations. Again, to the power transformer, we try to step it up the energy or the electricity we generate. So it goes to the transmission again. You can see all type of tower, all right. And then transmissions at the substation. So we do have the transformer again, and step it down to the distribution area or distribution substation, where we have all these distribution automation devices for protection, for switching, etc. etc. Right. So some of the end users of this energy, which is commercial, industrial, business consumers, we do have the factories, hospitals, all the big buildings, the huge buildings and all that, as well as the residential consumer. Okay, this is something like our home, okay, the housing area, all the villages, kampong, etc., etc. Okay, and then this is the grid system in Peninsular Malaysia in general. So you just focus on these two legends. I mean the purple, the what do you call it, the rectangular purple, as well as the yellow triangle symbol. So these two represents hydropower system or hydropower station, as well as thermal power stations. All right, so we do have many of them. For hydro, for example, so we have in Penang, all right, so some area in Perak, Pahang, as well as where is it? Okay, these two states. And then we come to the thermal power station, the Amani, all over the country. This part, for example, so in Melaka, in Negeri Sembilan, Kapas, Selangor, Perak, and all over the country. All right, electricity system in Malaysia. So this is what has been defined by Tenaga Nasional, our energy provider. So it says that voltage capacity in Malaysia, especially the transmission voltage networks, are divided into three, namely 500 kV, 275 kV, as well as 132 kV. So whilst the distribution voltage are 33 kV, so we step down from transmission voltage down to distribution voltage, 33 kV, 11 kV, and 400 or 240 volt. Alright. So however, in the case of certain parts of Johor and Perak, the distribution voltage may include 22 kV and 6.6 kV. Right. So when it comes to the distributions, so the voltage or the level of voltage is much lower compared to the transmission, because normally transmission voltage are being transmitted throughout long distance. That's why we need to have a much higher voltage to avoid those losses, voltage weakening and those kind of things. So supply frequency in Malaysia, so we have set to 50 Hz, which is also the common AC or electrical frequency all around the world. So basically, few countries, if I'm not mistaken, 43 countries, having 60 Hz. Some country like US, so they are using 60 Hz. By the way, it's up to the countries which value or which one they would like to use. All right. So now, okay, this one I have explained. Okay, this is the system we are going to analyze, or the system you are finally able to analyze. So how to analyze this system actually? So nothing here. We can simply say this is the generation part. All right, so we do have the steam power plant. So we have the power pump storage power plant, for example. So we have another steam power plants where all the generation, all the energy generated by this power plant has been distributed or has been transmitted into a grid line and finally integrated together. All right, so you can see the bus bar over here connected from the generation part to the transformer part, or step up transformer, for example. So we do have another bus bar, all right, for the connections before it goes to 25 km distance, another bus bar, all right, 10 km distance, and finally go to the consumer, etc., etc. All right. So this is to tell you that the system, even though produced or generated by multiple power plant, it still can be integrated and linked together. Right. So the brief idea on how it works is it being integrated. Okay, all right, now topic 1.1, single phase voltage generation. So this is basically how we generate single phase voltage generation. So you can see this first paragraph, or you can read the first paragraph. A single phase alternating voltage can be produced by rotating a coil in the magnetic field between N and S poles of a magnet. So basically we have a coil over here, which is represented in red and blue color. All right, so the slip rings, the carbon brushes to provide the DC current or supply. And then in the presence of magnetic fields, magnetic flux or magnetic field, which is generated by these two magnetic poles, okay, north and south. So we already know that. So the magnetic flux or the magnetic fields flow from north poles, okay, to south pole. So in the presence of magnetic field, so we do have our coil over here, which is rotating, okay, rotating, and in the same time carries certain amount of current. So the current itself will induce electromagnetic force. All right. So since alternate polarities of the magnetic field cut through the rotating coil, so the induced voltage will change polarity at the same speed as the rotation of the coil. So this is what happening here in this region. So we have again the magnetic flux. We do have the electromagnetic field which is produced by the current or the coil itself. So this induced voltage will change the polarity with the same speed as the rotating coil. So the alternator shown in figure is single phase because it produces only one AC voltage. Alright, so one AC voltage, so one single phase. Okay, we can simply conclude in that way. Okay, some of the YouTube you may see it later, or I will simply upload it in our class Google Classroom, and you can find the YouTube, or you can watch the YouTube over there. Okay, instantaneous voltage. So what can we understand with the term? So the EMF, or the electromagnetic force induced in a coil at any instant of time, depends upon the rate or speed at which the coil cuts the lines of magnetic flux between the pole, and this is dependent upon the angle of rotation theta of the generating devices. So figure will show the plot of the instantaneous value of the waveform, and also its direction varying according to the position of the coil within the magnetic field. So this is what we can see, or we can represent the illustration of the rotating coil. So we have this X symbol and dot symbol representing the direction of the current flow. So this is coming out of the page. So this is going into the page. All right. So we can see the rotating coil over here, which is rotate in the CCW, the counterclockwise, in again the presence of magnetic flux generated by these two magnetic poles. So we have south to north direction of magnetic flux, for example. So we do have the rotating coil or rotor within this region, and thus these two reaction of magnetic fields will cause the instantaneous voltage to be generated. All right. So it depends on the position of the rotor itself. So we can see, or we can say, at the horizontal area or horizontal position of the rotor in the beginning of the process. So we can simply say that the value is 0 over here. So as we move the coil with the X symbol, for example, up to this theta position, so now the value is increased, or the amplitude is increased up to this point. All right, so here, and as we go to this coil, for example, we go to N position, which is 90 degree, all right, from the base, all right, so or vertical position. So it now comes to the maximum peaks of the graph of the waveform. All right, so as this coil go further into this direction and back to the base position or horizontal position over here, so the value goes down to 0. So same goes to the other direction of the magnetic part or the magnetic region. So from N, now we move on to S. So the same behavior will occur over here, or the waveform will occur over here, but in the opposite direction or negative region. Okay, so then one complete cycle of this rotation, all right, beginning from here to this point, down to S position, for example, and back to the origin place or origin position. So it may produce a complete cycle of sinusoidal waveform. All right, so ranging from 0 to 2 pi of time. All right, and then so we can also represent all this into a electrical circuit. So we can have simply a Vp with the frequency as the voltage source. So we have the line over here as well as the impedance or the load. Right? Okay, again, the instantaneous voltage of the coil at any point in time around the full 300 degrees circle is given as Vt Vmax sine omega t. So Vmax is actually the amplitude, the maximum, the peaks over here. So this is Vm or minus Vm, or we can simply understood this as maximum voltage, positive maximum voltage and negative maximum voltage. So omega t, so this is represent the angular frequency actually. All right. So as we go here, so we can see Vt is the instantaneous voltage again, and then Vmax, the maximum voltage the coil can produce. So omega is actually the angular frequency in radians of the coil, or you can convert to 2 pi f, and time in seconds from 0 radians. All right. So additional note, in Malaysia, 50 Hz cycle per second is the AC frequency, but in some other countries, 60 Hz is the alternating current. But in most countries, majority countries, so they implement 50 Hz, as the alternating current frequency. So electric distribution system. So a distribution system transfers electricity from its source in the generator to loads such as heater, motors, or lights. So this is some of the application we use out of electricity. All right. So the system is identified by the number of phases, number of wires, and voltage between wires. So there are multiple, I would say, combination, numerous configuration of this uh, power system, okay, which is identified by the number of phases, gain number of wires, in fact the voltage between the wires. So distribution systems are classified according to the voltage used to carry the power from the power source to the distribution transformer or to the loads. Okay, and then this is again how we can understand the power system, or the transmission, distribution, from power generation, the power plant, and then transformer again. So we can see how it is being stepped up to the transmission line with all those towers, okay, carrying 400 kV, step down to transformer 275 kV, for example. It is reaching up to their final destination. As we can see, the voltage is now reducing down to 132 kV. It is something like landing down the voltage down to again 33 kV, 11 kV, and finally 240 volt for small commercial and residential area. All right. So somehow for light industry, medium factories, they use, or they requires three phase 450 volt. Then so of course this is different spec compared to different specification compared to 250 volt. All right. So single phase to wire system, how can we understand them? So this is actually the diagram of a single wire consisting of live conductor. So the coil over here, we can simply say transformer, for example. So the same wire we go to the and another end point, which is called neutral conductor. So these all lines, we can simply say single phase line, which is supplied to load. Then again, if we convert or represent this diagram into thicker circuit, we can simply say this is actually, or we can simply understand that this is really the voltage supply with its impedance or with its load. Okay, so a single phase two-wire distribution system has two wires coming from the generator set or from the secondary of a distribution transformer, with one of the wires grounded to this one. So this is simply, we can simply say this is actually a generator, or we can understand this is actually the secondary part of the transformer, distribution transformer, with one of the wires grounded to the earth. Right. So the grounded wire is also called the neutral conductor, this one. Alright, so the wire which is being grounded is normally called neutral conductor. So again, the second wire called the live wire or hot conductor. So the upper one, this one, so it's connected to the load. Alright, so this is actually connected to the load. So usually there is a difference of 230 volts in Malaysia between these two wires. Alright, so the differences of electrical potential between these 2 points, the live conductor and neutral conductor, is actually 230 or 40 volts in Malaysia. Okay. So any single phase we can understand, or we can simply conclude that any single phase, two wire, 230 or 40 volt load can be connected to both the live wire and the grounded wire. So this system supplies electricity for light bulbs, portable tools, and most equipment requiring low power. Okay, so single phase, three split phase power system. So this is how, again, we have a single phase, but this time around, so we do have the three wire system. So single phase, three wire distribution system is created by center tapping. So this is the keyword. All right, so center tapping. If I can change from laser pointer to highlighter. So this is the keyword, the center tapping. So to make the three wire distribution system, but still a single phase. So the coil winding of alternator or the secondary winding of transformer. So single phase three wire. So this is the keyword, three wire distribution system has one grounded wire over here. So one grounded wire and two live wire. Okay, the lower and the upper and the lower. All right. So line number one and line number two. So it is called a single phase system because there is no phase difference between the two available voltage. Okay. So between these two available voltage, 120 volt and another 120 volt. So there is no any phase difference. So figure below shows a split phase AC distribution system receiving is 120 or 240 VAC power from a center tap utility transformer. So this is the primary part of the transformer, carries 7,200 volts. So it is being stepped down into three wire system. All right, so line one, so neutral line two, where from line one to neutral, so it carries 120 volts. So neutral to line two carries another 120 volts. So we sum up between line one to line two, so we may get 240 volts. Okay, this is actually applicable not in our country, in Malaysia, but in US. All right, so the line to ground voltage half line, so you can read these notes yourself. So this is what I have been explained earlier, and including the application. So the single phase three wire system distribution system is commonly used to distribute electrical power to homes in countries such as US, but not in Malaysia, because again we do have two options, whether to consume 120 volt or 440 volt. All right. So we go figure below, so illustrates the phasor diagram of the output voltage for a split phase transformer. So this is what USA is applying. So we do have the transformer on the top of a pole. Okay, this is the pole. So this is where they locate the transformer. So this is the distribution line over here. This is the distribution line. So this is the transformer. So it carries, for example, 7,200 volt. Okay, so this is how they tap down hot clamp into fuse for the breaker or for the protection system. All right, and then this is the distribution transformer. Okay, so the two primary inputs of 7,200 volt, and this is the output. Okay, the primary and secondary. So output, we do have three terminals over here. So this is line number two or line number one. So this is the neutral point, and this is line number 2. So we do have either 120 volt or 240 volt for the selection. Right. So this is the phasor diagram. Okay, phasor diagram of the output voltage for a split phase transformer. So the line number 1, which carry voltage 1. So in between, in the middle, we have the neutral point, and then this is voltage number 2 from line number 2. Okay.